So, can you see my screen?
Yes, we can.
Okay. Thanks, Peter, for the invitation. Thanks for the introduction. So very happy to be here, even though it's virtual. So this is a joint work with Carol Bernard from Grenoble and VUB. And we gratefully acknowledge research support from CDI and Global Risk Institute. So let me start with motivation and look at this equation in blue. So this is famous, probably one of the most famous results in financial economics, first discovered by Breeden and Lietzenberger, and it relates the call option pricing function with the so-called risk neutral density. And basically it says that if I know call prices for all strikes, let's say from 0 to infinity, and if I differentiate this function twice, I'm going to have a risk neutral density. And this is forward-looking density, which tells me the future outcomes, future returns of the underlying. So there is some inconsequential constant, but basically it's a very simple, elegant, model-free result, which allows us to look at option markets to learn something about the future. So, for example, for S&P 500 index, currently I could have as many as 400 different options traded with the same maturity. They expire, let's say, in 1 month. So I have a dense set of strikes. And if I interpolate call prices somehow, differentiate wise, I will have the distribution of S&P 500 future returns. So again, this is well-known result, very beautiful, and probably one of the most commonly used in empirical finance, especially in derivatives. Yes.
Yeah, you just said you'd have the distribution of future S&P returns. I didn't hear correctly. If you said risk neutral, right? Or
risk
you meant
neutral. It's risk neutral.
There
is preference adjustment, but still, we could look, for example, what market thinks is going to happen, let's say, after elections, or we could extract implied probabilities of outcomes that Federal Reserve is going to increase interest rates over, next month during their next meeting. So there are a number of papers which use this information. It's forward-looking information from option prices. And if you have density, you can compute all kinds of moments. People interested in volatility, okay, you can get model-free volatility. You can get skewness, kurtosis, semi-variance, down variance, up variance, tail index, basically anything you want. Again, subject to this caveat that this is risk neutral one. So it also includes information on preferences. And as I said, conceptually, this is a very simple formula. There are some complications how you apply in practice, but there are a number of methods available currently which allow you to estimate this future forward-looking distribution. So, as I said, very beautiful, very simple, elegant, but only works in one dimension. So if I have options on stock A, I can learn distribution for stock A. If I have options on stock B, I can learn distribution for stock B, but there is no way for me to learn about joint distribution of A and B. And this would be extremely useful in a number of settings. Portfolio optimization, multi-asset derivatives, risk management, currencies. So this is important, but also very hard problem because we don't have multi-dimensional options. So we don't have options on A and B with all possible strikes. And if I'm interested in more than 2 assets, then it completely becomes infeasible because I will have multi-dimensional options. I would need them in order to extract this multi-dimensional joint distribution. In this paper, however, we claim that we could make some progress in this dimension. And we will construct a forward-looking joint distribution between D assets, and D will be 9. I will focus on sectors of S&P 500 index. And as inputs, I'm going to use the following information. I will use risk neutral density for each sector, which I will get from corresponding options for each sector. And then I will also have options on the overall market, the index, S&P 500 index, which is a weighted sum of D components. So I have information on individual distribution. I know how each stock A, B, C, D is distributed, but I also know how their sum is distributed. And I'm going to use a new tool. So this is the first time we introduce it in finance. It's certain combinatorial algorithm, which is called block rearrangement algorithm. So it's a key for our approach. And it will allow me to construct a probability model which prices all options on all underlying security and their weighted index perfectly. And it will be self-consistent model. You can use it if you want to price other options, like rainbow options, etc. But I'm going to, for the first time, take a look how the copula or dependence for the 9 sectors looks like. And I will show some interesting results. It's actually very non-normal. It's highly, highly skewed. So left tail is very different from the right tail. It changes over time. And because of that, I'm going to focus on 2 extensions of usual correlation. I will look at down correlation and up correlation. So down correlation.
Just have a clarifying question.
Yes.
These weights, omega 1 to omega D, are they fixed?
They're fixed today. Yes, today I know them. So
okay. And
they could change over time, but today I know them. There is a little assumption that if I'm looking at 1 month's horizon, I basically assume that they don't change much.
Okay.
I could relax it, but this is technicality.
And if it's all, if you don't mind, if I could ask, since we're talking about forward measures, could I ask a forward-looking question? I think you've already basically told us that there, unless you had the full space of cross options, you can't end up with a unique. I mean, you don't have a unique distribution that satisfies these various option prices. And so, what I would ask, if you could, as you go on, or at whatever point it is, what the methodology that you're using, what is it? What is it about? Which among many does it choose, if you will? Does that make sense? Am I correct?
Absolutely.
Yeah.
I'm going to address it. It's an important question. You're absolutely right. The market is incomplete, so the solution is not unique. I will answer your question in more detail, but let me give you kind of big picture overview at this point.
And one last question: do the omegas need to be positive, or can they be negative?
Positive. This is S&P 500 index, so those are weights of 9 sectors. They are positive, yes.
Okay, so they're positive.
I mean, for the algorithm, even that is not important, but let's not generalize it yet. It's not the main focus. So in terms of this uniqueness, basically, let me give you good news, bad news up front. So basically what our methodology allows us to do, to find a self-consistent probability model which prices today all options on underlying securities and the market. And currently for this application, I would have like 3,000 or 4,000 options, like 400 options on S&P and about 20 per each component. So I will find a model which prices them exactly simultaneously, which by itself is not an easy task to find this solution. Moreover, my approach will tell me when such solution doesn't exist, which is also quite useful because it actually tells me that there is tension, inconsistency between different markets. So there is potential arbitrage. So if I have time, we will talk about this. However, when the solution exists, again, because it's incomplete market, there are typically multiple solutions. However, our approach will choose a very good solution, the one which maximizes entropy. So of all possible solutions, And I think even a solution is already a good contribution. We actually will give you, in our view, the best solution that solves this problem. But let's come back to this issue if there are some questions a little bit later. So the outline, so this is the plan. We'll see if I can follow it. Literature review, then I will introduce this new algorithm. It's called block rearrangement algorithm. Again, the assumption is that I know distributions for individual components and for the weighted sum, and this will be used to construct the joint distribution. I will talk about the properties of this algorithm: stability, convergence, maximum entropy. And again, since it's a new thing that we introduce into finance, again, I'm going to go slowly and try to explain what exactly it does. It's actually kind of, in my view, very cool instrument. And then I will talk about this empirical application. As I alluded already, there are 9 sectors like finance, health, energy, and they do not overlap, and collectively they cover the universe of 500 stocks in the S&P 500 index. There are ETFs, spider ETFs, and there are options on them. So those will be used to get necessary marginal distributions, and then I will unleash this methodology. I will construct joint distribution every day from 07 to 17, and I will see how this dependence changes over time. Financial crisis, some other interesting events. Then I will focus on this down and up correlation, extensions of regular correlation. So the idea, I started to talk about this, but jumped. So down correlation is the correlation between 2 sectors, conditional on the fact that S&P is down, below its median. And same for the up correlation. And I will show that the 2 have completely different pricing. So there is risk premium. We know that correlation, there is a correlation risk premium for global correlation, the usual one. But situation is quite different if I split them and I look at the left tail separately from the right tail. It turns out that the left tail has extremely, extremely negative risk premium, much bigger than what is reported in the literature. But the up correlation has positive risk premium. So the risk premium changes sign. So
when you mentioned risk premium, could you just tell us what risk you're talking about?
So as usual in the literature, we are going to compare 2 counterparts, correlation computed under P from returns of underlines, and correlation that I get with my method from options. So risk premium is the difference between 2, P minus Q. And
so it's the thing that's variable is the correlation itself.
Yes,
is that right?
Yes, it changes over time and it's priced. And we know that regular correlation is priced. It has negative risk premium. However, when you split it in 2 pieces, one piece has a very, very much bigger negative risk premium in absolute value, and the other has positive one. And intuitively, it's like investors really don't like, I mean, when market goes down, the investors willing to pay premium for their portfolio to be diversified. So they don't like high correlation when market goes down. When the market goes up, investors actually prefer high correlation. They don't mind that everything goes up at the same time. So roughly this is intuition, and this is what I will keep for now. And then if I have time, I will talk about some trading ideas, how the methodology could allow you to make money out of it. Okay, so in fact, let me skip the literature. So there is extensive literature, and people basically try to compare index options with individual options to figure out a partial measure of dependence, average correlation. And next slide basically tries to explain conceptually the difference in our approaches. So the standard approaches, they start with this mathematical identity, which links volatility on the index and volatilities on components. And normally you would need to have a lot of pairwise correlations between A and B, A and C, but all those correlations are assumed to be constant. So the literature uses this equal correlation assumption. So single correlation is substituted. So then we have one restriction, we solve it, and we get option-implied correlation. So this is average pairwise correlation across all components. In terms of there are some differences. In terms of the volatility, in terms of sigmas, different papers, different approaches use different quantities. Some use Black-Scholes implied volatility, the money Black-Scholes implied volatility. So actually this is CBOE, they have correlation index, this is how they construct it. Some use model-free implied volatility, some use standard deviation of the risk neutral density. As a side note, this is the correct way to go. But the point is that of all options that are available, they use just one single statistic, single number. They summarize risk neutral density for stock A with its volatility somehow. They plug this in this equation and they infer single parameter of dependence, the average pairwise correlation rho. So what we are going to do, instead of single number, we are going to use information of every option. So if it's implied volatility skew, I'm not just using at the money implied volatility. I'm going to use the whole skew. I'm going to not enforce single restriction. Intuitively, what I'm doing, I'm enforcing a continuum of restrictions. So I'm making two random variables equal in distribution. So there are infinitely many restrictions that I'm intuitively using. Mm-hmm. And my goal is much more ambitious. Not just one single correlation. I'm going to try to extract everything, the whole joint distribution. But as a side note, our approach includes the standard approach as a special case, because as a special case, we also enforce this restriction. So our average pairwise correlation will be the same as you get in existing approaches. So if this is the only thing that you're interested in, yes, then you don't need our method. But if you use our method, you will still get the same answer. Okay, so now I'm going to spend a few minutes talking about this new toy, rearrangement algorithm. And initially, I'm going to explain how I solve auxiliary problem. And then in a couple of slides, I explain how it relates to the problem that I'm actually interested in. So suppose that there are D random variables, and I know their marginal distribution. And I'm trying to solve the following problem. I want to find a dependence, a copula, which links those D variables such that variance of their sum is minimized. So, for example, sometimes it will be possible for me to make the sum to be constant. And in statistics, it's called joint mixability. This is an important problem in operations research. But for now, let's suppose that this is what I want to do. I know distribution of D random variables. I want to find a copula or dependence between them so that they are as close to constant as possible. And this is how I'm going to do it. I'm going to construct this joint distribution or copula kind of numerically. I'm going to discretize every marginal distribution. So since I have distribution function, I just invert it, and I will have, let's say, 1,000 states which discretely represent this distribution. So for you to keep it in mind, in my application, I will have D9, 9 sectors, and each will be divided into 1,000 states, which I could make 10,000, but this is just to give you an idea what type of matrices I will be working with. And then I put all this information in this 1,000 by 9 matrix. So this is variable 1, this is variable 2, and this is variable D. And then within each column, I'm going to rearrange values. So I'm allowed to swap values within each column, but I'm not allowed to jump from column to column. And the goal that the sum of each row the row 1, the row 2, etc., that they all as close to each other as possible, meaning that the variance of the sum is minimized. Okay, so bad news. This is a very hard problem. It's NP complete problem. I mean, if I try to do it by brute force, I can try all possible permutations and find the one which gives me this objective function minimized. But in general, this is how many permutations I will have. Now think n is 1000, d is 9, so forget about this. So I need something else, and this is where I'm going to use recently introduced algorithm, which is called rearrangement algorithm. So this is heuristic algorithm, but it turns out to work extremely well. So for all practical purposes, it's almost like exact one. And it's based on very simple idea. So let me try to explain it. So what I do, I go one column at a time. And in a couple of slides, I will have a very simple illustration. I will actually show this method with 4x3 matrix. But the principle is the following. Pick one column, let's say column 1, and make it anti-monotonic to the sum of the remaining columns. So let's say I have 9 columns. I pick the first one. I have 8 others. I compute the sum of each row for the 8 remaining columns. And I make first column anti-monotonic to that sum. Anti-monotonic means if this one is sorted in increasing order, then this one will be sorted in decreasing order. And this is the way, it's easy to show, to reduce variance of the sum of the rows. So basically, if I do it for row 1, for column 1, then for column 2, column 3, I keep doing this very simple operation many times. Eventually, algorithm has to converge. Why? Because with each step, the variance keeps going down. It's bounded from 0, and it's a finite problem, so it has to converge, and in fact, it converges quite rapidly. And this is the idea of this rearrangement algorithm. So if I get to the point when the variance of sum of the rows is 0, so all sums are constant, so this is called complete mixability. So again, the idea in risk literature. So I basically found dependence between d variables, which makes their sum as constant as possible. So let me explain it with this simple example. I know it's getting a little bit abstract, but this is important to understand to what I do. Only 3 variables, x1, x2, x3, so shown here in this matrix, and there are only 4 states of the world. So it's like each variable could have only 4 values, 1, 0, 4, 6. So again, within each column, I'm allowed to change order of the values, but I cannot swap between columns. And my goal to make sum of this row, this row, this row, and this row as close to each other as possible. Now, it's such a small problem. I mean, most of you will be able to solve it in a few seconds by method of guess and trial. But again, I need an algorithm to do it systematically when I have big problems. So let me show how it works on this case. So again, I only change values within each column because they represent margin for one variable. So I change order, I'm not changing marginal distribution. But each row represents like state of the world. So it basically says which variables happened at the same time. So it basically gives me numerically dependent structure in this world. Okay, so this is how it goes. I started with all columns sorted from the biggest number to the smallest. So this is not complete mixability. This is actually the worst possible dependence for this problem because they're all monotonic. So the first sum is 16, 9, 3, 0. So they're all over the place. But this is what I'm going to do. I pick the first column and I make it anti-monotonic to the sum of the remaining two columns. So the sums are 10, 5, 2, and 0. So I want to sort the first column so it goes in opposite direction. So 10 now is paired with 0, 5 is paired with 1, 2 is paired with 4, and 0 is paired with 6. So anti-monotonic. If you can compute the sums, you'll see that they are much closer to each other. And this is the trick of this algorithm. So now I repeat the step for column 2. And it actually turns out that it's already, oh no, I need to flip 6 and 3. Then I do same for column 3. I'm going a little bit quicker, but you get the idea. So now this column needs to be made anti-monotonic to the sum of the 1 and 3, 1 and 2, 1 and 2. And basically the sums 3, 7, 5, 6. So this is the biggest one, so it's paired with 0. This is the second biggest, it's paired with 1. And at this point, you can check 7, 7, 7, 7, all sums are the same. So again, it's a very trivial example, but I just wanted to show that by doing this simple sorting procedure, in this case, I only need 3 steps to solve this problem. And when I have the solution, you can double check because no improvement possible. Each column is anti-monotonic to the sum of the remaining columns. Okay, so that was the idea of the rearrangement algorithm. We're actually using a more powerful version of it, which is called block rearrangement algorithm. Same idea. Now all the columns are partitioned into 2 blocks. And sum for the block 1 is made anti-monotonic to the sum of block 2. So basically, previously I did 1 column at a time. So it's kind of trivial partition, 1 versus d minus 1. Now all possible partitions are allowed. It turns out that you're actually getting faster and closer to the global solution. Okay, so I'm sure you're confused at this point, but let me explain why I need this auxiliary problem. Because in practice, I have extra information. I have marginal distribution for stock 1, 2, and D, but I also have distribution for their sum. And what I'm going to do, I'm going to construct similar metrics from discretized values, but the last column, I will put negative of the discretized values for their sum. So I have, it's enhanced metrics, there is 1 extra column, and the column are discrete values with negative sign for the marginal distribution of the sum. So now I apply block rearrangement algorithm. I'm trying to make each sum to be as constant as possible, but in this case, it actually will be 0, as close as possible to 0, if I have consistent initial data. So when I do this, and if sum of each row is exactly 0, I found this exact mathematical solution. So I found compatible dependence, which tells me that the sum of D variables is consistent with the alternative observation for the index. In practice, we will not get exact 0. There will be tiny deviation from it, but for all practical purposes, it will be negligible. So mathematically, we are finding approximate solution, but for all practical purposes, it's as good as the true one. So let me illustrate this procedure on more realistic example. So let's say there are 2 components, and they have risk neutral densities shown with the blue and green curves. So, and this is Black-Scholes world. So I have actually I have normal distributions, not even log normal. But suppose I got them from options. So I observe blue and green line. I also observe weighted average, sum of them, 1/2 x1 and 1/2 of x2. So think of those as risk neutral densities. I need to discretize them. So I actually don't need densities. I need distribution functions. So those are cumulative distribution functions. And I basically, you don't see this, but there are like 10 points. In reality, I'm using 1,000 quantiles. So I divide this into 1,000 pieces and I take those points. So basically I have 1,000 returns for each stock. I put them in the matrix, which in this case will be 1,000 by 3. I apply BRA, and this is how this matrix looks like. I'm looking at the first 2 columns. It's actually maybe easier to look at the joint distribution. I will show you 3 examples, and it will be like a little movie. Notice that marginal distribution do not change. This is by design. I'm going to keep my options for stock 1 and stock 2 unchanged. So their margins will be fixed, but the red line will be changing. And you will see that marginal densities stay the same, but the 1,000 dots, the scatter plot, keeps changing. So let me go back and explain. In this case, I assume that there is no dependence. So 2 stocks are orthogonal, and because of that, there is big diversification. So I have kind of narrow distribution for the sum. In this case, I have strong dependence. So the 2 stocks are highly correlated. So the red line now is more spread out. So this is the only input that I'm changing. So you see, if I go back, only the red line gets modified. So I'm getting a different column for the sum. And my BRA gives me a different distribution of 1,000 states. So again, think about the world represented by 1,000 different states. And I'm trying to couple them to say, in this state, this is what happens to stock 1, this is what happens to stock 2, and this is what happens to their sum. And ideally, they need to match. My final illustration, I'm using asymmetric dependence. So now red line is a little bit skewed. So it has wider left tail. This is what we actually observe in data. So the left tail is wider, thicker than the right tail. This is what happens to copula, and this is what happens to their joint distribution. So we see that our left tail has much stronger dependence than the right tail. And this is type of dependencies that we'll see in real data. In this case, the down correlation, the correlation when market goes down is stronger, is bigger than when the correlation goes up, when the market goes up. So in this case, down correlation is bigger than up correlation. And this is kind of to anticipate what is going to happen in real markets. Let me pause here. Any questions?
So, well, you've, let's say, minimized variance of a sum, and you know, when you can solve that problem, you've got joint distributions. Is that what you're going to claim is the joint distribution, or?
Yes. So basically, at the end of BRA, so I started as input with the matrix. I end up with another matrix, which is just a permutation of the original one. So same values, but just moved. I changed places. But this is the representation of the joint distribution. So I'm basically say there are 1,000 states in this world represented by 1,000 dots. And for state 1, the return for stock was, for first stock was minus 10%, and for the second was minus 8%. So each one state is not important. What is important is the whole cloud. So basically, I could move a few points and the distribution doesn't change that much. So this is one of the good things, like there are multiple solutions, but they all look like this. So if you look at them from far, it's the same scatter plot with very thin left tail and very wide right tail. But this discrete matrix, this is the solution to the joint distribution. So I get kind of numerical joint distribution, which tells me that in my world, there are only 1,000 states, which I can make 10,000, doesn't matter. And all of them equally probable so equal probabilities, and I know what happens in each state, and collectively it gives me the joint distribution.
I have another question.
Please.
Yeah. So initially, you were sort of telling us that multi-asset options don't really trade, and well, I want to challenge that a little bit. I mean, it's true in the space of listed options, or mostly true, although there are options on commodity spread futures, for example. So there would be two assets in there, or there are also options and futures, on the Nikkei and dollars. So we have the Quant, there would be two assets, the Nikkei and also the yen dollar exchange rate. So there can be a little bit of information on listed markets, but of course there's also the whole world of exotics, and that is OTC. So it's kind of not public, or transparent, completely transparent market, but you can have that. But just commenting that you're assuming that the sum, the marginal distribution, the distribution of the sum is known, and so I'm sort of wondering how you expect from your assumption that the information is not available. So how do you expect to have that information in terms of having the distribution of the sum available?
I'm not sure I got the whole question because it was a little bit.
Yeah. Okay. Let me interject.
No, but
So Sebastian, he's thinking not only does he see options across all strikes for individual stocks, but he also sees options across all strikes for S&P 500. Okay, so that's how he's going to get the marginal distribution of the sum.
Oh, right. Okay. So
exactly. So
right.
it's a limitation of the approach. I actually assume very liquid options. I need a very detailed information on each component and on their sum.
Right.
Sum is actually easier because index options are very liquid. We had data for 30 years to extract risk neutral densities for them.
Okay.
But yes, this is the assumption. I need this extra information to learn something about the joint distribution.
Yeah.
And
okay.
I think
So
you mentioned
clear.
something about currencies. Think about an example. So you have dollar-yen futures and options on it. You have dollar-British pound. You can construct risk neutral density for them. And then you have cross currency, pound versus yen. So you actually have, I mean, it's not exactly sum, but it's kind of product of two things. There is a way to formulate this approach for them. What you need: distribution for one variable, distribution for another variable, and distribution for their function. In this case, linear sum.
Okay. Thank you. Yeah. Thanks.
Yeah. So Oleg, my question is, like, I'm very impressed that you can find a dependence that minimizes the variance of the sum. But why should I believe that that is the dependence in the market?
Okay. So this is back to this uniqueness. So let me show. I will try to go quickly. So, I mean, because I do want to get to the empirical application. So this is from our previous paper where we kind of introduced the theory for this approach. I will show you one application which shows stability, accuracy, and maximum entropy of this approach. So again, I admit that there are infinitely many solutions, but the one that we find has the property that of all solutions which match observable data, it has the maximum entropy. So it's, in statistical terms, the most likely solution.
Maximum entropy and minimum variance are two different things. So
right.
you connect maximum entropy and minimum variance.
Right. But basically, like, imagine this little Sudoku puzzle, right? So 4 by 3. It's possible that there are several solutions. So you keep perturbing your rows, and there is one solution where variance is 0, another solution when the variance is 0. So there are actually multiple global solutions. What I'm claiming that of all those global solutions, I'm going to pick one, and this is, I'm not actually, it's a part of the algorithm. I'm not imposing this objective function because it's based on this randomization sorting. It's actually converges to the solution which has maximum entropy property. I know it sounds a little bit too magical, so let me show you a couple of figures. Maybe it will convince you.
Okay.
I'm going to do it in Gaussian case because for this case, I know everything. I know how the maximum entropy solution looks like. So I start with D random variables, all normally distributed, 0 sigma I squared. It's heterogeneous. Sigmas are from very small to very big. So they decrease from 1 to 1 over D. And I impose that on average correlation between them 0.8. So I'm going to run my BRA 500 times. And because it's heuristic and it starts with different initial conditions, it uses randomization, it actually gives me every time slightly different solution. So I want to see what are those solutions. It turns out that they are all in the same place. And of many possible solutions, they pick a very good one. So this picture, it's three-dimensional case, because in this example, my variances are fixed. And because it's Gaussian case, the whole model is characterized by 3 sets of correlations, rho 1, 2, rho 1, 3, rho 2, 3. So in this three-dimensional space, I have this like exotic fish plot. It represents the set of all admissible correlation metrics. So basically, I can pick any point here, and I get feasible correlation metrics, meaning it's positively defined and has correlation between 0 to 1. But because I impose condition that my average correlation is 0.8, I have this plane which intersects this exotic fish, and it basically says that only within this range, it looks like ellipses, it's not, only those combinations are feasible. Okay, so this is the set of those feasible correlation metrics characterized by 3 correlations, and any of them is the solution. So just trust me on that. So any point here gives me, so this is the multitude of the solutions. Any point, pick on inside of this ellipses, and it gives you the solution. So here you have 500 points, and they all cluster it in the middle. And what is special about this middle point? This is the point which maximizes the determinant of the correlation matrix, which is equivalent to maximum entropy. I do the same example, but I increase the discretization from 1,000 to 10,000, and they become even more clustered. So as I increase the number of states, it's a random algorithm. There's randomization involved. So it always gives me slightly different solution, but all those solutions, empirically, they are all very similar and all concentrated around the same point. In fact, yeah, this is interesting picture. So I know how the maximum entropy model looks like, and I see my solution, what correlation it gives, and compare to this maximum entropy, and this is how well it matches. So basically, this is the case of 10 components, so there are 45 correlations. Those are different values of those correlations, and the method basically pin downs, matches all of them. I do stability analysis. So I force my system start from wrong solution. So it's still global solution, but not stable one. So this is blue point. And then in this case, it's a matrix with 1,000 rows. I flip only 2 rows. So it's already solution. If I leave it like solution, nothing will change. But I perturb it a little bit, just 2 rows. And what happens? 500 points starts to move from initial condition to this stable one. Well, if I increase the discretization, this stability becomes even stronger, So my point is that there are indeed many solutions. We always end up with, if we have enough discretization at the same point, and then we start to look what's special about this point. And this is the point where entropy is maximized. I know I left a lot of outside, but this is kind of many solution. Any point here is a feasible solution, but we always pick one, and this is a good one.
Okay, I have a question. So, like we know option strikes are discrete in practice.
Yep.
And so I think what you could have done if you're maximizing entropy is maximize entropy subject to the constraint that you reprice every one of the discrete strike option prices that we see, as opposed to what you are doing, which is first sort of making up some option prices, if you like, so that we can get an entire marginal distribution for each underlying and also for the S&P 500, and then maximizing entropy. So you chose to, you know, kind of make up some option prices first and then maximize entropy when you didn't need to make up option prices. So
the method only works with distributions. I cannot work with option prices, all possible exotic convex payoffs.
Oh,
so,
is that right?
Yes.
Okay.
So because I work with those matrices and they need to be probabilities. So
okay,
I need to convert it into inputs that I can supply to my algorithm.
Okay, that's fine.
Yes, I'm basically, you're right. I'm filling the gaps. It's not so bad. Like, as I said, for S&P 500 index, I probably have like 400 options with 3 months to go. So it's very dense grid. And yes, I have options at 300 and 305. Well, I can basically tell you what's the option with strike 301, 3001 should be. But I create continuum of those option prices, and then I convert them into probability, and then I'm working.
Okay.
So I can talk a lot about this, but I want to get to the point how to make money. So, and I'm still a few slides that I need to cover. So quick summary. So there is a new tool which comes from operations research. It's based on this integer programming. There are some problems with it. It's not a convex problem, so there are multiple solutions. It's a heuristic solution, so I'm only guaranteed to get close enough, but I'm not guaranteed to get the global solution. However, with simulation, we show that this thing actually works extremely well. So yes, it's approximate solution, but it mathematically it's different, but practically it's the same. 10 to the minus 7 difference between global and approximation. So of many solutions, it picks a good one which satisfies this maximum entropy. So let's talk about the empirical application. So I already alluded to it, but this is my data. So there are 9 sectors. For them, there are ETFs, spiders. So there are consumer discretionary staples. The most important ones are financial, health, energy, and tech, the biggest ones. So for them, we have very liquid market, which started to trade probably like in 04, but in 07, I have enough options to extract risk neutral density. So this is where my sample will start. 07 to 17. I will do it daily. I will focus on 3 months horizon. So I will compute risk neutral density 3 months ahead. And this is like, I will do, for example, correlations, forward correlations 3 months ahead. I get sector weights from Bloomberg. So this is how it looks like. There are 9 sectors, but I'm showing only 3, finance, tech, energy, and the dark one is the SPX. So this is financial crisis. Financials started to go down. The rest did a little bit okay for a while, and then everybody started to follow. There are 2 dates which I'm going to show you what happens, and they are in the fall of 2008. So this is implied volatilities. Again, volatility increased a lot. This is just summary of the market. So this is how the pie looks like at the end of the sample, just to give you the biggest sectors. So tech is big, finance, health. And as I said, energy is another interesting one. So focus on 91 day, so it's 1 quarter horizon. Deal with the usual stuff. There are dividends, American style feature. So it's annoying, but it could be all fixed. It's not a big deal. I use my own method to estimate risk neutral density. By the way, I don't need risk neutral densities. I need cumulative distribution function. So instead of twice differentiation, I only need to differentiate once. So this curves of differentiation are not as bad as for risk neutral density estimation. So I only need one derivative instead of two. So again, D, 9 sectors, but I also have options on S&P itself. So it becomes 1,000 states times 10, 1,000 by 10 metrics. So this is what I use as an input for BRA. Each day I compute the solution for this variance minimization problem, and it gives me numerical joint distribution. And with the joint distribution, I can do a lot of stuff, and we actually have done many themes, tail indices, semi-betas, but for today, I'm going to focus on two unusual correlations, down and up. So here they are computed under Q, but I will have similar counterparts under P. And the definition is it's correlation between return on stock I, return on stock J, conditional on the market value being below its median. For practical purposes, I want my sample always divided into two parts, low returns below median and high returns above median. So just a quick sanity check. So the red line shows the physical correlation. So this is average pairwise correlation of 9 sectors. It starts in 98, 99. So for P, I don't need options, so I can go very far. And the blue line, this is what I get from options. So a couple of observations. When two samples overlap, the curves match each other quite well. So whatever I get from options and whatever I get from returns actually match each other quite well. So this is very comforting. Mm-hmm. So also, even though in my period, variation in the correlation is not that big, over longer periods, correlation could change quite a bit. So it used to be 10% after dot-com bubble burst, and sometimes it's like 90%. So there's quite a bit of variation in this pairwise average correlation. But again, red under P, so it's realized, and blue, this is what I'm getting from the options. Okay, so 2 days in the midst of the financial crisis. And I'm going to show how dependence looks like on those days. Now, my joint distribution is 9-dimensional object. It's a little bit hard to work with it. It's hard to visualize it. So I need to make some sacrifices. So I picked 2 sectors, finance, which is very exciting, a lot of going on, and utilities, which is very boring. So it's kind of 2 extremes. And this is September in 2008. And you can see, so basically there are dependence shown in 3 different ways. So this is classical dependence. This is dependence. It's easy to interpret because I attached normal margins. So it's kind of normalized dependence. So this is like, if all variables are normal, but dependence is not, this is how would a scatter plot look like. And this is the contour plot. You already see that correlation quite high. And the left tail is a little bit thinner than the right tail. So the dependence on the left tail is stronger. Utility is not that interesting, but still there is some dependence. And this is dependence between finance and S&P with the market. Let's fast forward less than 2 months. So it's November 20th. So the financial crisis starts to rage, become more and more problematic, and dependence become much, much stronger. So here now we are talking about correlations which closer to like 97%. The left tail, it's almost perfect correlation. Basically, if the market drops, it's one-to-one movements. Utilities, which used to be kind of boring, now suddenly also becomes exciting. But clearly, the left tail is much stronger dependence than the right tail. I do statistical tests on normality, rejected, easily. So there are several versions which focuses on skewness, kurtosis. Skewness is the biggest problem. So basically, for every day over time, we could say that dependence that I get from options is not normal because it's not symmetric, it's skewed. This is correlation metrics for 9 sectors on the first day. Instead of numbers, I give you colors. This is the second date. All colors became more purple. So it's basically, we are getting closer to 1 correlation. This plot, it shows down correlation versus up correlation, and for all 9 sectors. And this is 45-degree line. I just wanted to show that basically for any given day, the down correlation is always above 45-degree line, so it's higher than up correlation. So this is previous day. This is next one. They all moved toward this corner. They're closer to perfect correlation, but they still remain above 45-degree line. So this is big picture view. The usual regular or global correlation. This is what I get from options. This is financial crisis, the 2 days that we inspected. And this is down and up. There is always gap between the two. So down is always bigger than up. So there is this huge asymmetry between, again, left tail and the right tail. Which leads me to the next slide. And I think this is the most kind of interesting contribution to this risk premium literature. So I compute for every day option implied and realized correlations. So I start with global. This is what people already knew. Take the difference P minus Q. So this is our risk premium. Statistically significant, negative. Again, people already reported that correlation is priced and the correlation premium is negative, meaning that people don't like correlation, willing to pay money to hedge against correlation going up. Now I do the same thing separately for down and up. And basically notice that even under P, there is asymmetry. The down correlation is bigger than up correlation. But the symmetry becomes ridiculous under Q. And when I subtract, I get basically very substantial risk premium. Remember, I'm talking about quantities which are between 0 and 1. And this is how much mispricing I see for the down correlation. It's 3 times bigger than for global. And for the up correlation, I get positive risk premium. So it changes sign, and it's, again, double of what you get for global. So if I take the difference down minus up, and later I'm talking about down minus up correlation swap. So this correlation swap has a payoff, which is equal to difference between realized down and realized up correlations. And if you trade it, it again, historically would have performed quite well. But this is enormous risk premium that you get from this type of instrument. By the way, I should point out, if you're confused, that down and up correlations are generally lower than global correlation. This is mathematical fact. This is true even under normality, because truncated correlations, so if I have scatter plot and I take only left half of it, it will have correlation which is lower than the total scatter plot. So you shouldn't compare this number to this one, but you should compare down and up, because for normality, for all symmetrical distribution, they should be the same. And they are hugely different, especially under Q. So again, I already stated it before, but option markets tells us that investors don't, there are 2 types of correlations, bad and good one. When the market goes down, the correlation is bad. Investors don't like it, willing to pay premium to hedge against it. When the market goes up, investors prefer high correlation. They don't mind correlation to be high. So this is why risk premium changes the sign. Any questions at this point?
This correlation you're talking about, is it correlation between a sector and the S&P?
So this is pairwise down correlation. So I'm doing all possible correlation, finance versus energy, subject to market going down. I'll have many of them, and then I take weighted average of those 45 correlations. 45,
Okay.
36.
Okay, thanks.
So I'm trying to do it similar to existing literature, because the global, this is how people, this is the only thing that people could extract from options previously. And it's value weighted average of 36 pairwise correlations for global thing. Now I do similar one for left tail and the right tail. So this is just to show visually, you have implied blue and realized, global, down, up. Basically what I'm trying to say that this gap here between the two, it changes the sign. So this is the risk premium, and it's negative for down, it's positive for up. When you combine the two, the net effect slightly negative for the global. Then we investigate what is more important, margins or dependence? Because if you compute correlation, let's say global one, it's a function of the two inputs, marginal distribution and dependence. And we have a lot of interesting stuff going on. So I'd like to disentangle whether it's due to, let's say, skewness of the margins, because even for the sectors, I have skewed risk neutral densities, or it's due to non-normality of the dependence. What we show that it's all about dependence. So basically, this asymmetry between down and up correlations, 88% of it comes from asymmetry of dependence and 12% from asymmetry of marginal distributions. Same with the risk premium, because I have the whole joint distribution. Instead of computing Pearson correlation, the usual one, which depends on margins and dependence, I could compute instead Spearman correlation, rand correlation, which only, it doesn't depend on margin, it only depends on it only depends on copula. And all risk premiums are about the same size. So basically tells me the risk premium, the correlation risk premium that people studied, reported, it all comes for pricing dependence, not the margins. I know I'm going a little bit quick, but again, the bottom line, it's very important to properly model dependence, much more important than margins. It's highly non-Gaussian, non-normal, highly skewed, and this is where the risk premium is buried. So this is what causes the pricing. In fact, I know that some people may be skeptical about this numerical BRA procedure. So by inspecting how empirical dependence looks like, we suggested alternative model. We call it hybrid model. And what it does, it uses non-parametric margins, which I get from options, and it links them with the parametric parsimonious copula. We need to make copula highly skewed. So we use skewed normal dependence with 2 parameters. I'm not going to get into details, but this hybrid model, I mean, by construction, it cannot compete with our method. It's not as accurate, but some people feel more confident because they kind of understand what the model is. So it's, instead of normal dependence, we deform it in a certain way. We make it highly skewed. Margins, non-controversial because you get it from the options. You link everything and you get quite decent model. And most of our results, we confirm that quantitatively they hold even with this hybrid model. Okay, I'm starting to run out of time, but I wanted to get to this point. Trading ideas. And there are 2 of them. So the first one I already alluded. Basically, I'm saying that the pricing that we get from options tells us that the correlation risk premium changes sign, and down correlation is very expensive and up correlation is very cheap. So if you construct a down minus up correlation swap, so the way it works, for the next 3 months, you observe daily returns. You divide them, there are like 63 returns, trading days. You divide them into 2 groups. When the market above median and below median, for each group you compute correlation. So this is down, this is up. And the difference down minus up, this is the variable leg of this swap. So this is under P. We compute it under Q, and this thing is very, very expensive because it takes advantage of two effects, that the down correlation is very expensive and the up correlation is very cheap. So you kind of double this risk premium, and the risk premium is 5 times bigger than the global correlation risk premium. So again, if such swaps were available and their pricing was according to what we get from our methodology, this seems like it would have been a profitable strategy. But let me talk about something else, because I started with this, that our methodology can tell us when individual options are inconsistent with the index options. Such situation could arise. And how can we take advantage of this if it happens? So the basic idea, and some of this known in the bounds literature, but basically we have this universal property which says that because the payoff of options is convex, then option on portfolio is cheaper than portfolio of options if strikes are chosen appropriately. So we have this relationship, and this is true for any choice of weights lambda. And when you convert it into observable option prices, it basically says that call option on sum on the index must be less than weighted sum of the call option on individual components. Again, strikes needs to be properly matched. And you can try to test this inequality. So this is universal inequality for every choice of lambda. And again, imagine that you have 9 sectors, so you have too many possibilities you need to check. And there is an alternative approach. The alternative approach you can try to do, you can say, oh, the call price for the index may be bounded between 2 extreme cases. In this case, I assume that all my D9 variables are combinatonic. So I assume extreme dependence. They always go up and down at the same time. So margins are fixed, but I pick the most extreme copula, combinatonic one. And here, it's another case when I assume that my random variables are independent. So I have 2 bounds, upper and lower. The second one is completely model free. It should hold always. If it's violated, it's pure arbitrage. The first one, it requires weak economic assumption. So if it's violated, I mean, sometimes it could be violated, but it cannot be violated constantly. Basically, it's statistical arbitrage.
I mean, you've got an implicit assumption here that there's positive dependence.
Positive what?
Because like I'm saying, it's say that CS is below the independence result. Now, I wouldn't call that an arbitrage. I would call that a violation of the assumption that the constituents of the index move in the same direction.
Right. In fact, this inequality more interesting. This is where violations are found. So I'm actually finding the pure arbitrage. So let's not worry about.
Yeah. Okay. Okay. Fine.
But basically, the point is that I get margins from individual options, and I can link them in different ways. I look at one extreme that they're perfectly combinatonic, and the other extreme, I cannot make them anti-monotonic because there are many of them. So what I'm making them independent. So it's like the best diversification you can have. In practice, since everything is positively related, generally correlations are positive. So this seems still to be conservative assumption. But I agree, mathematically, there is assumption involved. Let's worry about the second inequality because this is what interesting. Mm-hmm. So this is what I'm doing. The same 2 days, I compute. So this is implied volatility curve that I observed in the market. This is what would have been implied volatility curve if I assumed combinatoric dependence, and this is independence. So those are two bounds that I just computed, and this is normal day. So I'm in between two bounds. I don't see any problems. I can look at the risk neutral density. This is out of the money prices, and this is normalized bounds. So this is upper bound, lower bound, but basically I'm in between, no problem. So this is the next day, which is a little bit more problematic. And the true implied volatility curve gets extremely close to this theoretical bound, but it doesn't cross it. So there is no arbitrage. Remember, on that day, on the left tail, I started to observe correlations approaching 1, but it's still not an arbitrage. I'm okay. However, there is my favorite day. I wrote a couple of papers on this. So the next one, this is flash crash day. And maybe it was not tradable because, I mean, it was crazy. All prices went out of line. But on that day, index options were so expensive that they were more expensive than individual sector options. Mm-hmm. So on that day, there was like about 10% mispricing. So this theoretical right inequality got violated. Mm-hmm. Again, it's potential arbitrage violation. You need to think about trading cost, all other stuff. But if everything is frictionless and perfectly measured, this stuff cannot happen. And it's not part of the paper, but we actually do find a few days which have this property.
Oh yeah, I suspect that there are some very large quant funds that are probably doing this. They're not necessarily, you know, they don't necessarily have this behind it, but I'm sure that there's a lot of arbitrage going on between you know, ETFs and their underlyings and sectors and their components, right? I mean, I think this must be a very rich target space for quant funds. That's an uneducated guess on my part. I
completely agree. But this is, if you want to look at this May 6, 2010 flash crash day. So this is, I mean, my algorithm still tries to construct probability model, but because there is arbitrage, it clearly screams that it's not possible to. So you see that it doesn't look right. Mm-hmm. So it basically has a tension to feed the left tail. And if you look at the objective function, it's very high on this day. So it basically says no solution. And this is basically diagnostic, which tells you that this is a problematic day. Okay, I apologize for venting over the time. So this is basically the summary. So we introduced a novel approach based on this new tool, which was developed in operations research. So we found a way to apply it in finance. So we introduced it for the first time. And I think it has very, very interesting properties. So again, depending how generous you are, but you could say that this is a generalization of Breeden-Lietzenberger to multivariate case. So it allows you to construct a feasible probability model which prices simultaneously all traded options on individual components and on the index. So there are a number of applications you can pursue, pricing multivariate options consistently with the vanilla ones which you observe. So let's say I need to price some exchange option on 2 sectors or rainbow option. At least I can find the price which doesn't contradict to all available prices. Empirically, we apply it to S&P 500 sector options, implied dependence, clearly non-Gaussian, changes over time. There's a huge difference between left tail and the right tail. It leads to down and up correlations differ from each other by factor more than 2. So again, standard models don't generate this type of skewness. So you kind of need to look for very extreme dependencies, copulas to have this property. I talked about risk premium, it changes sign, and we introduced this hybrid model. So the list of some of the possible extensions, we started to work on some of them, like pricing path-dependent multivariate derivatives. We actually got a little paper accepted in Review of Derivatives Research, so we kind of pushed this idea a little bit. But if you're interested, so the paper is available here, and thank you for all your comments. Looking forward to any questions.
Okay, thank you. Yeah, I guess we have quite a few comments.
Sorry, the line, I don't know, is it appropriate for me to ask a question or
yeah, go ahead, Sebastian.
Okay. So thank you, certainly, Oleg. It looks like a very interesting paper. There are lots of topics that are close to my interest, on average correlation and dispersion, trading, and so on. You mentioned also Breeden-Litzenberger. I wanted to mention that I have actually a paper recently with Peter and also Andrew Papanicolaou that is related to that. So Breeden-Litzenberger, if you integrate by parts twice, you get, Karin-Meden formula, which is replication of a European or any exotic European option with vanilla calls, and it turns out that multivariate extension is possible. And so that paper is on static replication, and it's actually also related to dispersion because I'm looking at a multivariate option, multi-asset option, really, that is the Euclidean norm of the prices. So it would be more like cross-correlation type of payoff. And there are, I see many connections with this paper that you're doing too. So yeah, just wanted to add this comment.
Okay, thank you. I'm super interested in this paper. Please send me.
I'll put the link maybe on the chat window. Yeah.
Excellent. Thank you so much. So, should I try to answer some questions in the chat?
Yeah, if you just take a look in chat and give it a try.
So I will probably go in random order. Does the rearrangement change the correlation of assets? Yes. So imagine that initially I sorted each column from largest to smallest. So I made them combinatonic. This would be the case of the highest correlation possible. Now, let's say I randomly permute them. I will probably get correlation close to 0. So this is the whole point of this rearrangement, because when I rearrange values, I change pairings of returns in different states. So I do change dependence, and that means I'm changing the correlation. So I could have anything from 0 to almost 1. So could you give us intuition for the M matrix permutation? So again, basically, the idea is that each column represents distribution for a single asset. If I just focus on one column and I swap the values, because the values are the same, they all have probability 1 over n, so like 1 over 1,000. So I don't change the distribution. The marginal distribution remains the same. So remember my scatter plot illustration. I get 1,000 points, they get moved, but the marginal distribution stays fixed. So this is what happens if I change values within my matrix. I respect the constraint that marginal distribution cannot change. But I'm interested in what happens row by row, because this is what determines the dependence. And this is what BRA allows me to do, to find of many permutation metrics, the one where each row sums to 0 or close to 0. Then I basically found a world where there is a probability model, and in each state, if I take weighted average of D components, it gives me the same return as the market, and it happens state by state. So I matched, basically, this is strong convergence. I matched 2 random variables, so their distribution are perfectly matched. So this is, kind of intuition for permutation of the matrix M. So let's see. Did you calculate correlations in physical and logarithmic coordinates? No, I'm using simple returns, because the risk neutral densities, yes, they could be converted, but it's easier to work with the simple returns. So options are written on simple returns as opposed to log returns. So some of the questions I'm not sure.
The last question is basically.
Yes, yes.
Yeah, the one from Shay Guan, he's basically thinking about multi-period, like you've been thinking single period, and I think that's
okay. Okay, so okay, maybe this helps. So I picked a fixed maturity 3 months, and this is kind of practical trade-off. I still have liquid options 3 months ahead, so I can get all those risk neutral densities quite accurately. But my constraint, I actually need to estimate correlations well under P. So for that reason, at least I use daily returns. So 3 months at least gives me 63 returns. So, but in principle, I could do it for any horizon. I have complete model months ahead. I have complete model 3 months ahead, 1 year ahead. As long as option market gives me detailed information under Q, I could do actually much more than under P. So yes, I could construct a term structure of the joint distributions for each maturity for which options are available. 1 month ahead, 3 months ahead, 1 year ahead. Any other questions?
Well, I have a comment. So I like the maximum entropy approach that you're using, but I've seen other people use it, and a common feature, let's say, when you're maximizing entropy is that there's a lot of discontinuity. So for example, if we looked at the copula that you end up producing by maximizing entropy, I'll bet it's not very smooth, and so, a thought is to build into the criterion smoothness as well. So do Tikhonov regularization, say, so maximize entropy, but subject to smoothness penalties, so like have a trade-off between smoothness.
So let me make 2 points.
Okay.
First of all, we don't explicitly impose maximum entropy criteria. It becomes a byproduct of this procedure. In fact, when I started to work on this project, I said, okay, this sounds cool. You have this constructive way to generate probability model, but it's heuristic. And every time it gives me different solution, it's no good. So you cannot construct index in finance, and every time you run the algorithm, you get different number. So I started to check, and I see that it gives me always the same value, which I don't understand. Like, why? There are many possible solutions. I'm using 3-dimensional example. I do Gaussian, and it keeps giving me some correlations which I don't understand because it's heterogeneous case. You don't have a general idea what maximum entropy is. So I started to think about, it took me a while to figure out that I get correlations which maximize determinant. Then I realized that it's related to entropy. So we started to dig deeper and figure out that this is indeed the case. Sometimes when you show it to physicists, they say, I mean, obviously it's maximum entropy. You keep sorting the system, it has to converge to something which is the most likely outcome. Now, what else could it be? So for them, it's obvious. But again, we are not imposing this criterion. It's a byproduct of this sorting procedure. And what I'm constructing, it's already not smooth. It's numerical copula, which has 1,000 discrete points. Each point has probability 1/1,000. And what it does, it tries to find scatter plot, which is as smooth as possible. So if you have 2 clouds separated, this is not a high entropy. If you have a nice smooth cloud, this is maximum, this is high entropy. But your candidate model still needs to satisfy all other information that you have, all other constraints. So you need to find a probability model which fits every marginal distribution individually and on the market. And then if you have some room, you pick the one which is the smoothest one. So my simulation showed that there is no problem. It actually gives very, very beautiful distribution. It's never rough.
Okay, thank you. All right, good. All right, let's wrap up. So the last comment in the chat was thank you, Oleg, and I completely agree. Thank you for that. It was extremely interesting. I think you'll have no trouble publishing this. It's, you know.
Yes, very good piece of research.
And thank you, Peter, for setting these up. And thank you, Peter.
Just a reminder. Sure, there's no meeting next week because it's Thanksgiving, so we'll meet again in 2 weeks, okay? All right.
Thank you, Peter. Thank you, everyone. Great conversation.
Yay.
Yay.